Okay, let's look at this physics problem. It's a classic physics problem. Inverted spherical bowl with a piece of ice on the top and it's sliding off, and what point does it lose contact? And I've already done this. Okay, so let me go over the first solution. I'm actually going to do it at least 3 times. It's going to be awesome. So here's my first solution, and I'll link the video down below. This is just a picture. This is not a video. So what you do is you look at where does the normal force on this ice cube go to 0 as it slides down this curved path, this circular path. It's in a circular path. And then you can find so you set up the radial forces of normal force minus the component of the gravitational force, and that has to equal to the centripetal acceleration, v squared over r, mv squared over r, which you can find the velocity based on work energy. And the end of the story is I got an angle of measured from the vertical of 48.19 degrees. And again, you can go look at the video. I'll link it down below. And I'm actually pointing down below, and you can't even see it. I don't know why I'm doing that. I'm pointing down below. So let's do this another way. So we really have 2 kinds of forces. We have constraint forces and we have calculated forces. So let me start with some calculated forces. Here's one. This is the gravitational force on the surface of the Earth. If we know the mass and we know the gravitational field G, then we can calculate the gravitational force. Here is the gravitational force, but the better gravitational force due to objects where we can change the distance and stuff like that. So if you want to look at the gravitational force at the space station or on the moon or things like that, or between the moon and the Earth, that's the gravitational force. But again, if I know r, the vector from one object to the other, and I know the masses, I calculate it. Boom. This is the Lorentz force. So if I have a charge moving in an electric and a magnetic field, I can find the force. It depends on the velocity. The vector velocity depends on the magnetic field B. It depends on the electric field E, but I can calculate that force. Here is the air resistance force. This is complicated because it depends on the magnitude of the velocity. And then rho is the density of air. A is the cross-sectional area of the object. C is a drag coefficient. V hat is important, just like in the gravitational force with the r hat. That is there to make this a vector, right? That says this air resistance is in the opposite direction as v hat. V hat is a unit vector in the direction of v. So it has no units. It has a magnitude of 1. It's just a direction. This is the spring force. So this says that the force due to a spring is a vector. Again, that's why we have that L hat. So maybe this picture will help right here. Here's a picture. If I stretch the spring, if I have the vector L hat is the distance from the point. L would be the distance from the point of the spring to the end of the spring. L0 is the unstretched length. So the more I stretch that, the difference between L and L naught, the magnitude of L, multiplied by the spring constant K, would tell me the force. And then it's in this force is in the opposite direction of the stretch, and that's why that negative sign is there. So those are all calculated forces. I can actually calculate those forces. But what about the normal force? I can't calculate the normal force. There's no equation for the normal force. You can determine an expression for it based on the situation, but it's not a calculated force. The normal force pushes to keep that block from going through the bowl, and it does whatever it needs to do. Okay, it can't pull. That's why the ice loses contact, but it doesn't. There's no equation, so you can't. And that's bad. It makes it more complicated to deal with problems like this, but we're going to do it anyway. So what we're going to do is make the spring force, the normal force, a spring force. So here's the idea. What if the bowl and the ice are like a spring? And so if that's the case, as the ice overlaps with the bowl, then it compresses the bowl and the bowl pushes back. And so you could set up the following expression. If the radius or the vector position, the magnitude of the vector position from the center of the bowl to the ice is less than the radius of the ice, then there's going to be a normal force. And that normal force is just like a spring. There's some spring constant, and then instead of L and L naught, I have R and the radius of the bowl. It looks just like that other equation. And if the radius, the magnitude of the position of the ice is greater than the radius of the bowl, then the normal force is 0. Okay? And so you can imagine this bowl pushing the ice away, and the ice temporarily loses contact, but then it falls back and hits the bowl again until it never does that again. So that's what we're going to do. So here's how we do that. We're going to break this into a numerical calculation. In a numerical calculation, if I can calculate the forces, which now I can cheat and calculate the normal force, I can calculate the gravitational force, break the problem into tiny steps, I can assume those forces are constant over those time steps and use that to find the change in momentum. So I'm skipping some of the steps here because I've done this several times, and I'll link a good video down below where I go over as much detail as possible in a numerical calculation. But here's the basic idea. Number one, calculate the force on that ice. And so again, we have the gravitational force. The normal force is either going to be 0 or some spring-like thing, but I need to calculate that normal force. Once I have that normal force, I can use that to update the momentum. This is straight from the momentum principle. F net is the change in momentum over change in time. So if I know the initial momentum and the force, which I just calculated, multiplied by delta t, I can find the new momentum at the end of that time interval. Now I can use that momentum and divide by the mass, and that's like the velocity. And I can use the definition of average velocity, change in position over change in time, to solve for the new position based on the old position. And yes, this really should be the average, but if my time interval is small enough, it doesn't matter. For step 2, that assumes the force is constant over that time interval, which is not, right? But we're going to do it anyway. And then I can update time, move it to the next time interval, and then just repeat this whole thing over and over and over again until something happens, until the ice loses contact or until the ice hits the floor, whatever I want, or for a certain amount of time. And this is exactly what I'm going to do. I'm going to do this in Python, and I'm going there right now, so I'll see you there. Okay, here I am I'm using Trinket, which is implementation of GlowScript. If you haven't seen this, you probably haven't watched my videos, and that's cool. I don't hold that against you. So let's say bowl, ice, not lice, ice problem. Let's save this before we move on, and let's just start getting to this. I'm gonna go fast because I'm excited. The thing I'm thinking of first is I need this G vector, the gravitational field, and I do want this as a vector. I don't want to put this as a scalar because this is a vector problem. Next, I need the radius of the bowl. Let's put it at 10 centimeters. We can change that later. Now let's make the bowl. So bowl equals sphere, position equals vector 0, 0, 0, and the radius equals r. Now let's save it. Whenever I do something like that, I like to run it just to make sure that I'm on the right track. And there's my bowl. You can rotate this around. That's what's nice about GlowScript v Python. Now I need to make the ice. So ice. I've already thought of a problem. If I put the ice exactly on top of the bowl, nothing will happen. Something will happen, but it has to be tilted just a little bit so that it starts to move. So I need to pick my angle theta. Let's say theta is half a degree. So 0.5 times pi divided by 180, that's half of a degree. And that's measured from the vertical axis. So if that's the case, then when I make my ice, I'm going to make it a sphere. And I'm going to do that because I don't want to, if I made it a rectangle, I'd have to worry about rotating the rectangle and stuff. And I just don't really care at this point. We can make it look better later. Actually, let's say it's the position equals bowl.pos. Bowl.pos is the center of the bowl. I'm going to add the position to the center of the bowl, which is at 0, but I'm just trying to be a good person here, okay? So if I move the bowl, this will still work. Plus vector r times cosine theta, right? Because I'm measuring that angle from the vertical axis. So the x component would be, the x component would be sine theta. See, good thing I thought that out. Sine theta. Then the y component's going to be r times cosine theta. And the z component's going to be 0. Not negative 0. Okay, the radius is going to be, let's put it at 0.02. I'm just guessing here. I definitely want it to be something like yellow. So color equals color.yellow. And then I want to turn on the trail, make trail equals true. Let's save it and run it to see if we can see the ice. Okay, because you see the problem here. I'm putting the ice at the surface, so it's gonna actually extend below the surface of the sphere. But as long as I can see it, that's fine. Okay, it's kind of big. Make it a little bit smaller. It doesn't matter. I mean, that's just a visual thing. Okay, so there's my ice. Yeah, I know. It looks silly. That's fine. Okay, now I need some other things. I need the mass of the ice. Ice.m equals 0.100, let's say 0.1, 10 grams. I need the momentum. Ice.p equals vector 0, 0, 0. So it's going to start from rest. What else do I need? I need that spring constant. That's that spring constant that depends on whether the two things, how much it pushes apart. So I'm going to pick K equals 1,000. I don't even know if that's good or not. Now I need my time, T equals 0. dt times step equals 0.001. And I can change those. I think that's good. Now, let's start off with while t is less than 0.4. I'm just picking a value, okay? Because I know how to increment t. If I pick something else like while the ball is greater than some y position, it may never get there. And I may end up with the code that runs forever, and that's just not cool. Okay, in my loop, the first thing I can do is rate is 1,000. So since I have dt is 1/1000th of a second, if I put rate at 1,000, it won't run any faster than 1,000 calculations per second. So this would be in real time. So it should only take 0.4 seconds to run. If things get complicated, it may slow down, but it won't go any faster than that. Okay, so what do I need to do next? Here's the first thing I'm going to do. I'm going to put this n equals vector, spell it correctly, 0, 0, 0. So every time I go through the loop, I'm going to start off and say, okay, the normal force is 0. And then if it's below if the position is less than the radius of the sphere, then I will set it up to something else. So that's the first thing I need to calculate is the radius, the r vector from the center of the sphere to the ice. So r equals ice.pos, which is the vector position of the ice, minus bowl.pos. And if you just did ice.pos, it would work because the bowl is at the center as at 0, 0, 0. But that's just not cool. So now I can say if the magnitude of r, I can't say if r because that's a vector. If the magnitude of r is less than the value of r, then do the following. And I can choose my equation that I had before. N equals negative k times the magnitude of r. This is right from that presentation I just did. Minus r, and then have to multiply by the unit vector r so that it's a vector again, right? Because k is scalar, mag r is scalar, radius of the sphere is a scalar. So this is times norm r. That makes it pushing away. Let's just check, right? So if it's r, the magnitude of r is less than big R, then we'll have, this will be a negative number, right? And then I'll multiply it by a negative over here. And then r is pointing away from the sphere, so the force would be pushing away. So that's good. Okay, that's it. Now I can calculate the total force. F equals ice.m times g, that's the gravitational force, plus the normal force, which may or may not be 0, right? It depends on that previous step. Now I can go into step 2, update the momentum. Ice.p equals ice.p plus f times dt. Now I can update the position. Ice.pos equals ice.pos plus ice.p times dt divided by ice.m. And then update time. T equals t plus dt. I think that's good. I'm saving it. And let's just run it and see what happens. Okay, that looks pretty good. It moved. See, it moved? Okay, let's let it go for a second and see what happens. Okay, it left. So I think things are working. It's running too long. So let's do this. Let's calculate. Let's run it until theta is just about 0 degrees. So I need to calculate theta after I've moved the ice. So if I think about the x component of r and the y component of r as this triangle, just like I did before, I can say theta is equal to the arctangent of the x component, r dot x, divided by the y component, r dot y. And now up here, I'm going to say while theta is less than, and I don't want to go to exactly to pi over 2, so I'm going to say 0.95 times pi over 2. But if it did that, if I said as long as it's less than that, once it goes down below the x-axis, it's going to be negative, so just go on forever. So I'm going to say and theta is greater than 0, then do the following. And let's see what happens. Okay, it did lose contact. It's kind of hard to tell because the sphere is so big. Let's make the sphere a little bit bigger, smaller, the ice. So let's say 0.01. Yeah, that looks good. I just want to find that angle right there. Let's try making a graph. Let's add a graph in here. I won't put the axis labels on there yet because I'm not sure what I'm going to graph. So F1 equals G curve. Color equals color dot blue. Actually, I know what I'll do. Let's make two graphs. F2 equals G curve. Color equals color dot red. And I want to plot the trajectory of this, and let's just see what happens. So the first thing I'm going to do is plot the trajectory of the sphere, which is kind of weird. So let's say I'm trying to decide how to do this. Let's say theta temp theta, t theta equals 0, d theta equals 0.01. Yeah, that's fine. And then I'll say while theta is less than pi over 2, what I'm going to do is, I guess I'm going to make a graph, so I don't need the rate statement in here. So what I'm going to do is to calculate the vector position of the surface. So I'm going to plot, let's plot, let's say r temp equals vector r times sine of temp theta. This is kind of dumb. I shouldn't be doing this. R times cosine temp theta 0. And then I can plot f2 dot plot the x component r temp dot x, r temp dot y. And this should just be a circle. And then need to update theta. Temp theta equals temp theta plus d theta. Okay, I don't have a good feeling about this. Yeah, see, did something wrong. Temp is not defined. R temp. See, I knew in my mind this is a bad idea, so I made a typo. Okay, I think I put it in infinite loop. Let's just get. Oh, stop it. Okay. You got it in infinite loop, so I'm just gonna delete this. Delete that whole thing. Bad idea. I knew it was a bad idea, and I did it anyway. Okay, so let's just go down here and let's just plot the trajectory. So let's just go down and say f1 dot plot r dot x, r dot y. Let's just see if we can tell. Okay, I like that. Okay, that doesn't tell us the angle. Okay, but you can see something really important there in that that oscillation at the beginning, that's because the mass was shaking up and down as it went below the sphere and got pushed back up. I can't get the angle from this. Let's plot the angle theta versus the compression r minus r. How about that? So let's do this. I want this on the vertical or the horizontal axis. let's do theta, and I'll do it in degrees. Theta times 180 divided by pi. And then this is going to be mag r minus r. That seems weird. Okay. I'm trying to decide what the best thing to plot would be. As long as I get it kind of working. Okay, so here it's not compressed. It's mostly on the surface. And it leaves somewhere around here, right? So this says it leaves right around 40 degrees, which we calculate as 49 degrees. So what about this? What if I put this at, make a smaller time step, make it run faster because I don't want to wait forever, and let's see what happens then. Theta, what the heck? Oh. How did I do that? I'll put that right there. Okay, so now it looks like it leaves around, still around the same value. I think it's working. I think I just have to adjust my parameters here. Maybe my spring constant's too high. Let's make this 500. Let's just see. Because if the spring constant's too high, it's going to push it away and it won't come back in time to get it. I think my best solution is to make a smaller and smaller time interval, but see, now it's too low. So I like that. Let's go back to 5,000, 1,000. Let's make it 10,000 just to see what happens. Okay, there you go. So it leaves right around that. I get the right answer. So that's the position that it left at, because the position between the radius and the sphere changes. It's not 0, and it's 48.7. So I think that's close enough, and I'm pretty happy with my solution. I'm not pretty happy with my plotting, but I'm pretty happy with the solution. Now, here's one thing that we could possibly do, and I'm not sure it will work, but I want to try this later. Now that I have a value for the normal force, couldn't I calculate the frictional force on this? And so I'd have ice with friction and find out what surface it leaves. Oh, but wait, I did want to try something else. What if well, you can try this. I'll link this code down below. What happens if you change the mass? What happens if you change the radius? What happens if you change the gravitational field? These are the two things, the gravitational field and the radius, I said did not matter for the angle that it leaves. So you could try changing those and see what happens. But this, like I said in the first problem, this is a classic physics problem. We solved it with work energy and forces. This is solving it with a numerical calculation, and I'm going to solve it with the Lagrangian method, but I'll do that fairly soon. But I just want to see the same problem solved multiple ways. Okay, I'll talk to you guys later.